in our discussion today, we are going to consider the Faraday's laws of electrolysis. Now, we should understand that we need an acute relationship between the quantity of electricity passed through the solution and say I represent that with Q, and the amount of the substance that is deposited at a particular electrode or dissolved from the electrode or evolved if it is a gas. Like we have seen that if I take the aqueous solution of copper sulfate as an electrolyte, and suppose I am using the copper as the electrode, anode as well as the cathode. And I am taking the aqueous solution of copper ions and sulfate ions. Now, in the aqueous solution of copper sulfate, which is dissociating into the copper as well as the sulfate ion in the aqueous solution, we anticipate here this copper to go to the cathode, the negative electrode, and grab the electron from there to get deposited as the copper metal. So, copper metal is deposited on the surface of what? This is deposited on the surface of the copper cathode itself. So, we can say here overall the weight of the electrode increases. Now, coming on to the anionic part, which would naturally go to the anode. You know that the bulky ions such as SO4 minus 2 has more discharge potential, hence we have the OH minus ions to readily participate in the oxidation to give you the oxygen gas. So, you have seen here that copper plus 2 had been converted into the copper metal, which is deposited on the copper cathode, whereas O2 gas is evolved at anode. Now, I want to bring out the relationship between the amount of electricity that has been passed through the solution and the weight of the substance that is deposited at a particular electrode. Now, it has been said by the Faraday's laws that the amount deposited, dissolved or evolved, if I consider that as W, is directly proportional to the quantity of electricity Q which is passed through the solution. Now, when I am replacing this proportionality with any constant, I call this equation as the Faraday's laws of electrolysis equation, which is being used to find out the weight of the substance that is deposited. Now, let us understand little bit about this Z. The constant is referred as electrochemical equivalence. This electrochemical equivalence, which is represented by Z. Now, how do you define that? Now, you can see from this equation that Z is equal to W provided Q is equal to 1 coulomb. So, what I mean to say that we can say this as the amount of substance deposited, dissolved or evolved when 1 coulomb charge is passed through the solution. So, as per this Q equal to 1, Z is nothing but the W. Now, we understand that charge of 1 mole of electrons, charge of 1 mole of electron is 6.023 into 10 power 23. This many electrons we do have in 1 mole, and the charge of each electron is, you know, this many coulomb, 1.602 into 10 raised power minus 19 coulomb. So, the charge of 1 mole will be, this is the charge of 1 electron, this is the charge of Avogadro number of electrons, turning out to be 96,500 coulomb. So, 1 mole of electron we refer as 1 Faraday charge, which is numerically equivalent to 96,500 coulomb. Now, there is another definition related to this Faraday. Now, I call this as 1 Faraday. Now we understand that 1 Faraday is the amount of charge required, the quantity of electricity, the mole of electron that need to be passed through the solution to deposit, dissolve or evolve 1 gram equivalent of any substance. Hence we can say that you know that 1 gram equivalent of substance is equal to equivalent weight many grams of that particular substance. Now we do understand here that the equivalent weight, which is represented as E, is equal to molecular weight upon the number of mole of electron involved in the redox process. So here on the whole you say that 1 Faraday is equal to 96,500 Coulomb charge is equal to E gram of a substance deposited, dissolved or evolved, right. You said 1 Faraday is numerically equal to this many Coulomb and is equal to qualitatively this many grams. So therefore the electrochemical equivalent, that is the amount of this substance deposited, dissolved or evolved per Coulomb will be equal to this much, this many grams. So that's what we call as Z. Now when I am putting this in that equation, W equal to Z into Q, that is E divided by 96,500 into Q, or we know that rate of flow of charge is what we call as current. So when I am substituting this Q in Coulomb with current in ampere and time in second, I will be getting this relationship. Now for the electroplating purpose, that means one metal depositing on the surface of the other. For example, cadmium metal depositing on the surface of mercury. Then in that case this equation would slightly alter and we write it as the surface area, thickness of the coating, density of the metal that is coated during the electrolysis is equal to Z into I into T or Q. So we should understand that this is surface area coated, this is thickness of the layer and this is density of metal that got deposited on the surface. So here we know that surface area into thickness will give you the volume. When I multiply the volume with the density, I am going to get the mass again. So this is the first law of Faraday's electrolysis. From the Faraday's first law we understood that the amount of the substance deposited, dissolved or evolved is equal to this much. So when I am writing this equivalent weight of that substance this side towards the weight, I am going to get this relationship. Now keeping this relationship aside, what I will do is I will take different electrolytic solutions in different containers, and we have to understand that all these containers had been connected in a series. So when I am connecting this in a series, on the whole that the equal amount of electricity had been passed. Now when I am connecting n number of electrolytes in a series, we understand that the quantity of electricity passed through all the solutions is same. Suppose I have taken here the aqueous solution of silver nitrate, say here is copper sulphate, and for example here I have taken the aqueous solution of H2SO4 itself. Now we understand here that when I carry out the electrolysis process here, the silver metal get deposited and nitrate ion being bulky, we can't expect it to undergo any sort of oxidation, therefore giving a chance for the hydroxide ion to undergo the oxidation to give you O2. Now coming back to this electrolyte, we understand here copper plus 2 its discharge potential is low, will be deposited as copper on cathode, and here also the OH minus ions will be evolved, will be converted into the O2 and O2 will be evolved at the anode. Here we have the H plus ions to give you the H2 gas is evolved, and likewise here the O2 gas is evolved at the anodic side. So therefore here as per the second law, when the quantity of electricity passed through all the solutions is same, from second law of Faraday we ascertain here that the gram equivalents of all substances deposited, dissolved or evolved is going to be the same. So, here when I pass the equal amount of current through the series connected solutions, the amount of the substance in terms of the gram equivalents are going to be the same. So, here when I write it in the interpreted form, where we can say W by E equal to constant, or W 1 by E 1 equal to W 2 by E 2 equal to W 3 by E 3 and so on. So, here we understand that this particular thing had been kept constant because we have connected this in a series. So, now we say weight upon equivalent weight will give you the gram equivalents of all the substances that are deposited is going to be equal. So, whether it is the silver deposited, oxygen liberated, copper deposited, anything, the gram equivalents are going to be equal. So, now when I am taking this equation, I can find out the weight of any other substance which is deposited, dissolved or evolved at a different electrode of a different electrolytic solution, or even I may be asked to find out the valency factor. I mean to say the molecular weight divided by the valency factor. When you are substituting, you are getting the equivalent weight, that term is involved here. So, this equation is considered to be very important as far as this examination is concerned.